Okay, we are going to move to the next talk. We have here waiting two speakers. We have Maria Mannone and Davide Rocchesso. Let me hope I have also pronounced this right. They are both from University of Palermo, and they are going to talk about quantum sound and the sound of Quanta.
Okay, thank you so much. Yes, I confirm that the sound is correct. So just let me, okay, share the presentation here. So thank you so much for being here. I'm gonna talk about our research dealing with quantum mechanics, the basics of quantum mechanics apply to human voice. And yes, and this is a collaboration with Davide Rocchesso. In this research, we were inspired by the pioneering work by Dennis Gabor, which was the same guy who won the Nobel Prize for the discovery of holography or invention of holography. So already in 1947, Gabor tried to describe sound by using the basics of quantum mechanics. And in particular, he defined the concept of quantum sound called phone as the unit area cell in the time frequency plane. And it's called phone according to phone in ancient Greek. In addition, we are not only interested, of course, in sound, but also in human voice, because we, as humans, we can use our voice as a probe to investigate the world of sound. In particular, it's particularly interesting the research field of vocal imitations, because voice can catch some essential features of sound. So, for example, here you see an example of car. Here the sketch of a spectrogram, and here the sketch of a vocal imitation. As you can see here, of course, the spectrum, vocal spectrogram is different. Of course, there are more passions, this human voice. But the voice like sketching these main curves and trends. So it's a powerful and cheap instrument to make research as well. That's not a car. She's Renata Tebaldi. She's a famous opera singer, maybe the worst enemy of Maria Callas. Here we have a kind of different spectrogram because, of course, we have this vibrato in correspondence to like octave here, also an octave jump in O mio bambino caro from Gianni Schicchi. Here, we can try to describe this phonation component as like the vibrato wave thing, the phonation, as, for example, as a Z component. The turbulence that is sketched here in this way might be the X component, and the myoelastic is like more noise component. We can call it Y component, is not really present here because usually opera singers are trained to emphasize phonation with respect to other components of voice. And we can start from these hints to start defining what we call the QVTS, the quantum vocal theory of sound, where actually we have the space, we have phonation as the Z-axis, turbulence, and myoelastic pulsation. Little by little, we can start recovering some essential concepts from quantum mechanics, applying them to the study of human voice. In particular, as the first feature, you can see here the block sphere. So let us start with phonation up, phonation down, Z-axis. Here the turbulence. And for one side, we have low spectral centroid, and here high spectral centroid. And the Y-axis can be made to correspond to myoelastic pulsation, slower and faster. So actually, we can describe a phone as a quantum state of sound in the space of voice primitives. In a couple of presentations ago, it was mentioned the problem of silence. So here we can have silence approximately in the center of the sphere. But moving forward, we can start developing, writing down eigenvectors, eigenvalues, and all mathematical machinery which is needed to practically make quantum mechanics out of that. So we can start with the vertical, with the z-axis, what is called computational basis 01 by quantum computing folks. So here we use U and Z, pitch up and pitch down. And again, eigenvalues, eigenvectors, here a nice projector for state up, here for the state down. The Pauli matrix for sigma Z. So if we have a phone that is only a superposition of pitch up and pitch down, we can write in this way. And here we have the probability amplitudes to measure respectively up or down. And here, the expectation value for sigma Z. The same thing can be, of course, developed for the other two axes. So if we apply the Hadamard gate shown here, so we can obtain, of course, the Hadamard basis, which is usually denoted as plus and minus. And here we can indicate that as R and L, respectively high frequency turbulence centroids, low frequency turbulence centroids. Sigma X is sigma X here. So here sign plus, sign minus. Again, projectors, eigenvectors of these bases. For the y-axis, we do accept suggestions because we still don't have a name, so we just call that complex basis, because as you know, we just use the sigma y with the imaginary unit, and usually people denotate this basis and this arrow respectively counterclockwise and clockwise. For us, there are faster Mayo pulsation and slower Mayo pulsation. And as I said, that's the complex basis. So, but we want to hear some sounds as well. So we can start with an example of phonation and myoelastic pulsation, which we can investigate as signs, and here as pulse trains. Actually is like the transient component here. So this is a sketch of a spectrogram with some approximately sound. So here the thick line is indicating the most salient pitch. And here these vertical things are representing an almost regular train of pulses. In more general case, we can also add noise. That's the original audio sample. And here the computer-made spectrogram, as you can see here, like the most salient pitch, which is almost steady, and vertical trains. So another basic concept, of course, of quantum mechanics is operator commuting. So here we were interested in finding, for example, if the order had any meaning here. So for example, if we start from an audio file and we first perform a measure of the noise component, which is the stochastic component in sound signal processing software. By the way, we used SMS tool developed at the University of Barcelona to implement practical calculations, which are using science for the phonation component, stochastic component for noise. So if we first of all perform a measurement of noise, then a measurement of harmonic, that is phonation component, actually we get a different audio samples, different one if different from the audio sample we obtain if we just make the inverse. First a measure of harmonic and then stochastic. Thus, these quantities are not commuting.
I en l'altre se li ha posat un tel. La vaca és cega.
That's the original audio. Okay, As you can hear and see, they are pretty different. And by the way, that's the value of the commutator. Another basic concept is the density operator. So in the left of this book, you can see the density operator. It is just a projector for a pure state. And here the trace or rho square is equal to 1 if you want to be sure that it's a pure state. And here we have a mixture. In our studies, it's a more like epistemological mixture, because here we can consider just one phone of sound. Here we have multiple phones which are superposed. So it's like some kind of mixing of sound. And here we have a mixing of states. And of course, this is trace or square or rho is less than 1. I'm not talking here about separability, but of course, this is a fascinating topic, because for the sound signal processing, there is the big problem of source separation. So maybe it will be interesting in the future to use quantum mechanics also to this aim. Voice and sound are developing through time. So we are interested in building up some kind of time evolution of phone. A very first simple choice is just considering just to have a closed and isolated system, so no time dependence for the Hamiltonian. Everything, forgot to say that in general we need a unitary operator. So you dagger just give me the identity matrix. And if we consider some kind of not realistic situation, closed and isolated system, we just have this expression. Everything seems nice, but unfortunately, nature is not going in that way. So actually, we need a time-dependent Hamiltonian. To move forward our investigation, we might think of an analogy. So we might imagine the phone as a spin immersed in a magnetic field. So you can see here a sketch of a static field, and this is the Hamiltonian. However, this field is not something really static, because there are some interaction that the overall field is changing itself over time. And actually we can in particular thinking of some kind of restoring forces acting on sound. And these forces can come from like sound production context, inside an analogy with speech co-articulation. But we can solve our issue if we consider a piecewise Hamiltonian. So like in each slice of time, we have an independent age of time. But of course, by considering also all these slices, we get an evolution. We propose this writing where we have a time-dependent yet still commuting Hamiltonian. And here T is included in this exponential decaying factor, where K, the damping factor, indicates co-articulation features. And S, this is a nice time-independent Hermitian matrix. So how can we evaluate this matrix? We can consider this structure, the structure of the static field, and we can evaluate the elements of this matrix by performing measurements of pitch, phonation, of course it's blue speech, noise and effects in the surrounding sound. And finally, that's the time evolution that we get, and this is our time evolution operator. To make some more music, we can be inspired by Bach. So I think all of you know this theme. La sol la fa la mi la re do re mi fa la si do re mi fa. Okay, that was the beginning of Toccata in Fugue in the minor, BWV 565. So we used a piano sample from of this sequence. We made the short-time Fourier transform to extract the most salient pitches here. And we used that form of the Hamiltonian to try to reconstruct the time evolution by considering as a phone, starting phone, just the initial note. Here, first of all, the system is detecting the lowering melody in the sequence and a little bit rising here. But then after reaching the lower octave, the system is finding, just detecting the repeated A in the perceived upper voice with some small kind of glitches here, because something here is not perceived as pitchy. But if we take the Bach piece and we immerse that within some noise, okay, that's what we obtain. I didn't say that each time that we perform this analysis, there is some little change, because of course it's some kind of probabilistic measurement. So we of course have some fluctuation. So when we perform this measure with this kind of noise amplitude 0.1, that's what we get. We have some scratches here and there, and we have more easily detected A. The landscape is quite different if we have a higher noise with 1.0 amplitude. This is a classic example from auditory scene analysis. We have two glides and we have bars of noise here. And usually people are perceiving some sounds in between as a tuning, there's a sound tuning effect. So people might perceive here the V or the good continuation shape according to different conditions. So if we consider, for example, the pitch up as our phone, we can also perform here the Hamiltonian time evolution. What we perceive here is the green line is indicating the phonation component, which is pretty clear for the first part of the graph. Then we have here some oscillations, and here this is perceived not as pitchy, and here is a bit fluctuating in correspondence to the bars of noise, and then it's going down. Look at us here again. That's what we obtain. It's again the original example. So in this case, we can also consider the concept of mixture of states if we consider not only the higher pitch as our phone, but if we consider a superposition of pitch up, pitch down, and noise. So in this case, that's what we obtain. So it's pretty clear, the lower pitch that is rising here, then the noise, the oscillation again, and then the pitch up going down, and this small yellow dot is only a trace from this lower line moving. And this is the graph of the amplitude. So pitch down is pretty, as you can see here, pitch down is pretty evident here. Then we have fluctuation due to the noise, and then the pitch up is more clear in the side, and the pitch down goes down. That's again the example we heard before. And here we also performed another Hamiltonian evolution from a mixed state, where this time we consider pitch up, pitch down, noise, and myoelastic effect. So that's how that sounds. So in analogy with digital audio effects, we can talk of quantum audio effects for this analysis. To end this presentation, I can propose just a sketch for a vocal improvisation, which of course might be implemented with some suitable code. Here we can use the block sphere as a score. And here you just see a list of instruction for 2 vocal performance. So being inspired again by Bach for the 2-part invention, we can think of 2-part quantum invention. So the first voice, if, for example, performing some pitch down with piano loudness and turbulence with forte loudness, and the second voice is here in the center, just silent. And then we have several sequences which can be mirrored as in the classic counterpoint style. So you can see here that what is performing, the first voice here is performed by the second voice here, and again in this case. And then maybe they can end with pitch up and pitch down, so we can imagine an octave difference or whatever. I'm grateful to you for your attention. This is our emails and some gentle reference to affiliations and geographical origin as well. And this is some drawing that I titled Quantum Sphinx, being inspired by quantum computing, quantum mechanics. I'll be glad to answer to your questions.
Thank you, Maria. That was an incredible presentation. First of all, I need to really congratulate you for these beautiful slides that were hand-drawn, and that's really a nice touch. And we don't have questions in the Q&A, so I like to ask people, the attendees, for interact with us within the Q&A section. And while we are waiting for questions, that really, well, that presentation really was really interesting for me, that since I'm working with quantum digital audio representations, it was really the completely opposite of my approach, which was getting the sound itself in a quantum state and looking at the sound itself as a quantum state. So it's really up for a quantum music information retrieval algorithm, and something that really it's really inspiring. Let me see if you have any questions. Well, so we actually have a lot of compliments. First, really, it's a really nice work. So let me just think that if I took it straight, you are decomposing the voice. You are actually looking specifically into voice sounds, right? And then you are decomposing it in 3 directions, or 4 actually.
We are considering 3 directions. So an analogy with X, Y, and Z used for example, the block sphere. Of course, if we might be interested in possibly other parameters, I can't imagine now which ones, but they might be. Of course, we might like extend the block sphere to something like more than 3-dimensional one, of course. But the basic idea should remain the same. And performing the measurements along each axis and considering like the sound through superposition of information along this axis. So we are kind of trying to catch somehow the complexity of human voice by decomposing through some components.
Yeah, that's probably the hardest part. First, you need to detect the human voice in a piece of audio. Then you need to separate it from the rest. As you mentioned, the separation. But oh, we got a question. Let me see. Do you have any suggestions for using the quantum vocal theory of sound for the use of making vocal imitations with the voice? This in contrast of using QVTS to measuring vocal imitation with the voice?
Oh, thank you for this interesting question. So for the use of making vocal imitation, in principle, we can run like two different kind of analysis. So for example, we have a original sound sample. We can perform a vocal imitation, so we can make an analysis as we made, for example, with the sound glides or with the Bach example, just of the original sample, and then make the same analysis with the vocal imitation. And of course, we can compare both of them and see if there is something common, and I do expect that there are. The advantages in directly focusing on the human voice is that it's kind of more synthetic. It's like you might look at a picture of a complex landscape, or you can look at a sketch of the landscape, because when you make a sketch, it's like filtering out a lot of information and focusing on some essential thing. And that's actually what human voice, because we can make like visual sketches, we can perform vocal sketches, and that's the usefulness, because they're simple to treat. There's also a cheap instrument, and still allows us to gain important information. Maybe also, I would imagine that also like the computational time for like complex and long sequences might be like much more simple with respect to the original complex audio file, I can imagine. I see also the question, the future direction. Wow, that's so cool. Another possible direction of development is thinking of the entanglement. Because yes, in relationship with the problem of source separation. So in considering, because here we just consider single phones, even when we consider superposition, we just had single phones superposed, but we might consider phones with multiple phones, as like the 0, 1, 1, 0 for the entangled states, and keep doing the research.
Yeah, and if you have multiple phones, you can actually separate them and make a lot of things.
We can try. We can think of, for example, partial trace. And this is done in quantum mechanics. So like you can separate the state that you're analyzing from the what you consider being the bath or the environment. So I wish something similar can be done in this case. So for example, we have like a complex or choir, we just wanna hear one precise voice. So we consider the state and then everything else just the environment, and we just make the trace.
Okay, I'm just reading another question that I saw in the chat, not in the Q&A. Could you comment on what does the uncertainty principle would correspond to in this picture? And if I might have some representation, what is the uncertainty principle?
Yeah, sorry, I was reading the question about sound identification. Is it this one? Oh, that's another one, okay.
No, it's another one from the chat, actually, not from the Q&A session.
Oh, nice, okay.
The person is really asking for you to elaborate a little bit more about the uncertainty principle in your model.
Yes,
in your representation model.
Yeah, oh, thank you. Yes, that's interesting, because we can think, for example, a very precise measure with respect to, let's say, to phonation, like a less clear information regarding, for example, the turbulence. Actually, I think we had made time ago some experiment in this direction, which I did not include in the presentation, but yes, it's incredibly working. And also I see another question for the question answer and questions here. Yes, I think we can detect specific patterns, because actually we can just do that with by analyzing spectrograms of human voice and just comparing them, even maybe performing the measurement with respect to the phonation components. So we filter out, for example, the turbulence information, And we can, of course, easily use the techniques for audio comparison here. And yes.
Okay, so I would like to thank you, Maria and Davide, for this great work about representing a new kind of representation for sound. And we are going to the next and last.